In this media, you will learn about pneumatic pilot valves and pneumatic amplifying relays. When the imbalance detection system is most sensitive, self-balancing mechanisms are more accurate. One such self-balancing mechanism is the fictitious pneumatic laboratory scale. Reduction in the size of the orifice can make a plain baffle nozzle mechanism to be extremely sensitive. On the other hand, the smaller orifice will also limit the rate of airflow available to fill the bellows, thereby slowing the response of the system. Alternatively, the baffle nozzle mechanism can be made more sensitive by amplifying its output pressure with the help of some other pneumatic device. The self-balancing system is made even more precise by making small changes in detector output to bring about bigger changes in the amplifier output. We need to find a pneumatic device similar to the electronic transistor that lets one signal control another. Analysis of pneumatic mechanism and its electrical analog is as shown. The distance between the plug and the seat changes with the upward and downward movements of the control rod by an external force. By extending the control rod and adding a second plug seat assembly, we can improve the sensitivity of the pneumatic mechanism. The mechanism thus obtained with dual plugs and seats is called as pneumatic pilot valve. With the movement of the control rod, both variable restrictions change in complementary fashion. This combination of changing in the opposite direction of two restrictions leads to much more aggressive change in output pressure as registered by the gauge. A pilot valve of the similar design changes the directions of the two plugs and seats. The only functional difference between this pilot valve and the other one mentioned above is an inverse relationship between control rod motion and pressure. All that we have managed to accomplish at this point is to build a better baffle nozzle mechanism. In order to achieve a pneumatic equivalent for an electronic transistor, we need to allow an air pressure signal to control the motion of the control rod of a pilot valve. This can be accomplished by adding a diaphragm, which is a thin disc of metal sheet. The elasticity of the metal allows the diaphragm to function as a spring if the diaphragm is taut. Therefore, the applied air pressure input will exert control over the output pressure as shown in the figure. The pilot valve will be turned into a pneumatic relay with the addition of an actuating system to the pilot valve. This pneumatic relay is equivalent to the electronic transistor. The pneumatic relay can be classified as a direct acting relay because it has a direct relationship between input and output pressures. As the gain of any electronic amplifier circuit, the gain of any pneumatic relay is defined as the ratio of output change to input change. For example, consider the change of input pressure to be delta 2 psi, when an output pressure change is delta 12 psi. Then the gain of the pneumatic relay is 6. The performance of the pneumatic system can be improved by adding a pressure amplifying relay to the force balance system like our hypothetical laboratory scale. Since the nozzle's back pressure is amplified by the relay, the response of the force balancing bellows will be aggressive to any change in baffle position than it is without the relay. Many pneumatic instruments with high sensitivity amplifying relay have been designed by the Foxborough Corporation. A different style of amplifying relay in some of the pneumatic instruments is adapted by the Fisher Corporation. The direct-acting relays are further classified into bleed-type and non-bleed-type relays. Non-bleed-type relays, like Fisher relays, have the ability to choose both the supply valve and the vent valve simultaneously. On the other hand, the bleed-type relays, such as the Foxborough relay, has a ball and stem valve that could never close at the same time. Thus, you have learned about pneumatic pilot relays.